we're going to look at 2064. So let's just look at a picture of 2064. And this is an incline. And there are two masses. And there's a pulley. So we have this one mass, which is called big M. And then the other one is little m. So they want everything here in terms of variables. And the reason this is capital M and this is lowercase m, because this mass is going to be greater than this mass. Why is this important? When we end up doing our free body diagrams and we're going to be using Newton's second law, F is equal to ma, the most important part after our free body diagram is establishing our sign convention. So when I look at this picture right off, I'm just going to draw to myself that it's moving in this direction. And why is it important? Because when I sum Newton's laws, I want my sign convention, the sign convention is the key to physics, to be going in the direction that's positive. So on the incline, my sign convention here is going to be that's positive, this is positive. Okay, so that's the key there. So what I'm going to do next is I'm going to draw my free body diagram. Well, the big M is going to be the easiest because the big M, when I draw my big M, the only forces acting on it are, I have my weight acting down. So for this one, F of G is equal to big mg. The tension, remember this is positive, but I'm not summing yet. And then going up, I have my tension. Now, this block is a little bit different. So I'm going to draw the block the way it appears at an angle like this, little m. And remember, I have the tension here. So one pulley is one rope, which means one tension. So that tension is equal to this tension. So that's this tension. Now, this block, I have the weight going down. So remember, the weight always acts straight down. So this weight, F of G, is little m times g. The frictional force acts parallel. Now remember, this is moving this way, so friction acts, and on the exam, if they ask you to label the forces on your free body diagram and do them at point of contact is going to be like this on the surface. Now when I end up summing forces and doing my components, I'm not going to draw them at point of contact, I'm going to draw them from center of mass. And then my normal force, again, is here. It's a contact force, so my normal force is going to be like this. So this is if I was asked to draw my free body diagrams of all the forces acting on the point in which they do. Now, the next thing I want to do is, I know that all my forces, in this particular case, I want them to go perpendicular and parallel to the surfaces in contact on this block, which is going to be like this. Okay, so what I'm going to do now is I'm going to redraw this, and I am now, the tension's going to be the same. The normal force is going to be the same because that's perpendicular and parallel to the surfaces in contact. The frictional force is going to be the same, but instead of the weight, I'm going to draw my weight into its components. So let's look at it real quick. I'll do it in pencil. And remember, here's my surface. So what's going to happen is this, instead of the weight, first I'm going to go perpendicular, and the direction of this is important. So this is going to be FGY. From the head of this vector, I'm going to do the tail of the other. These two have to be perpendicular, so it's going to be parallel. And this is going to be FGX. And then this angle here, theta, is similar to this angle here because these are perpendicular. Now I'm going to redraw, I'm going to figure out what are FG. So now I'm going to redraw this, and this is going to be FGY, and then this is going to be FGX. And the direction of these force vectors is important when I sum forces because I'm going to be looking at the direction. So I know that FGY is equal to, it's little m, so it's going to be mg cosine theta, and FGX, and why is it cosine? Well, if I look at my triangle here, FGY is adjacent to this angle. So that's why we're using cosine. And then FGX is opposite the given angle, so it's mg sine of theta. Now in this particular problem it says mass little m is located on an incline with a coefficient of friction mu and is attached by a string over a pulley to a mass big M. The pulley is massless and frictionless and the string is massless. Determine the following in terms of, so everything in this problem has to be in terms of little m, mu, theta, and any other constants we have. Okay, so what would another constant be? A constant would be like little g or something like that. Okay. Now, part A, so part A says find the maximum mass that will allow the system to remain at rest. So that's also important because at rest means that when I sum forces, this is a static problem, and this means that the acceleration is 0. Okay, what we're going to do today is we're going to do this as a system. We're going to apply Newton's second law to the whole thing. Okay, so we know that Newton's second law, so I'm going to say summation of F of a system, SYS, is equal to the mass of the system times the acceleration. But we know that this is equal to 0 because it's at rest. So we know that summation of the system is equal to, so what are the forces that make up this system? So now I'm going to look at my free body diagram. So let's look at this. So we have FGM, big M. Now remember, when you're looking at this, we have the tension going this way and we have the tension going the other way. Okay, so the tensions are going to cancel each other out. So we have FGM minus FG little m. So now I'm going to look at this free body diagram. So what do I have? I have FGX. So FGX is going to be mg sine of theta. So it's FGM sine of theta minus f of f is equal to 0. And now I'll substitute in what all these things are. So this is negative, and this is positive. This is doing it as a system. So now this is going to be big mg. This, and I should have written what this was FGX. So in case I skipped a step, that's FGX. And that's that. This is equal to little mg sine of theta minus f of f. Well, what is f of f? Well, I know that f of f is equal to mu times f of n. How do I know that? Because mu is equal to f of f over f of n. So now I'm going to set, instead of f of f, I'm going to write mu times f of n. But what is f of n? Well, I can also do to the side here, if I sum forces here vertically, and I'll do it real tiny over here, I'll say summation of f of y is equal to ma, which is equal to 0. So now I'll say that f of n is equal to fgy. So f of n is equal to fgi, which is equal to, up here, mg cosine theta. All right, so now I'm going to substitute that in here. So I'm going to have this is equal to mg minus mg sine of theta minus mu times mg cosine theta. All right, so what I'm going to do is the first thing I can do is I can cancel the g's. Okay. And then I'm going to rearrange all this, and I want to solve for big M. So I'm going to get big M is equal to m sine of theta plus mu m cosine of theta. And then I can simplify this and get m is equal to little m. I'm going to pull out the m, sine of theta plus mu cosine of theta. And that's my final answer. All right, now when I look at part B says to find the tension. So what I'm going to do is I'm going to look at this free body diagram because it's the easiest. And I'm going to sum forces down. I'm going to say summation of f of y is equal to big MA. And then I'm going to go ahead and I'm going to look at that and say what forces. I have the weight acting down, mg minus t. And again, that's going to be equal to 0. So T is equal to big M times G. Now, I could also use some forces on the other one, but that would take a little bit more time. Then for part C, it says to find A. So what I'm going to do is I'll look here and I'm going to sum forces and I'm going to say the string breaks. So I no longer have a tension because the string breaks. So the tension disappears, and I'm going to sum forces. Now the block is going to move this way. So when I look at my free body diagram for part C, my free body diagram is just going to be FGX going this way. There's no tension, but because it's moving this way, the frictional force acts the opposite way like this. So I'm going to say summation of f of x is equal to MA. And I'm going to now look at this and say FGX minus f of f. This is positive, this is negative, because now my sign convention is going this way, is equal to MA. Now I'm going to substitute in my values mg sine of theta minus mu mg cosine of theta is equal to MA. I'll cancel my m's. And then I just rearrange the equation. G sine of theta minus mu g cosine of theta is equal to A, and then I'll pull out the g. So g sine of theta minus mu cosine of theta is equal to A.